Hello, everyone. I'm Mike. Welcome to an INC Chalk Talk. Sanjoy Dasgupta is a professor in the computer science department here. He's been doing algorithms work for quite some time. He's done some work with the late Chuck Stevens about olfaction and data structures. And he's going to be talking about his new work in representations. So please enjoy the talk.
Okay, thank you. So let's see. So as Michael was saying, I'm a computer scientist. I work mostly in unsupervised learning and algorithms. And in the past few years, I've been doing a little bit of work that is in neuroscience. And today I'll be talking about something that is with somebody who was a PhD student here, Chris Tosh, and he is now at Sloan Kettering. So, so what I'll be talking about is this particular representation that is from the fly olfactory system. And I'll be going into a little bit more of the detail later on, but just at a high level, the starting point is a sensory input that's relatively low dimensional and dense. And then it's blown up to much higher dimension using a random linear mapping. And finally, it's sparsified. And so the final representation is a sparse, perhaps binary representation. And the question is, what is this thing good for? Often we try to move in the opposite direction, to start with something high dimensional and move to something lower dimensional. And so what exactly are the benefits of a representation like this? So this particular line of work started almost a decade ago when these two guys just called me from out of the blue. So Saket Navlakha and Chuck Stevens were both at the Salk at that time. And they just called me one day and said that there seemed to be random projections in the fly's brain. And you're a random projections guy. Can you help us understand what's going on over here? And I was a little surprised to hear, the idea that there could possibly be random mappings in the brain. And so I was sort of intrigued. And so I started talking to them, and sure enough, there were random projections. And we started looking at some of the circuitry in the olfactory system from an algorithmic viewpoint, just trying to understand what algorithmic tasks are being solved here. What are the algorithms being used? Are they solving traditional computer science tasks? And can they, in fact, be brought back to computer science? And we actually found, methods for a whole lot of problems, from nearest neighbor search, novelty detection, habituation, approximate counting, most recently continual learning. And in each case, these algorithms were actually very simple and were quite easy to bring back to computers. And the key thing is that they all really depended crucially on this high dimensional representation. In fact, that representation made the algorithms almost trivial. And so we wanted to study the representation just by itself in a little bit more detail. So here is a schematic. So there is the, a sensory input here at the olfactory receptor neurons. And then in the mushroom body, in the Kenyan cells, it becomes a much higher dimensional representation. And so let me just briefly go into a little bit more of the detail there. Okay, so there are many olfactory receptor neurons, maybe over 2,000 of them, but they're just of a few types, like roughly 50 types. And in the glomeruli, the copies of the same type essentially get averaged. So this is a place where you can actually read off the sensory input, and it's about 50 dimensional. And it's dense, so each of the signals is sort of like exponentially distributed. So it's a 50-dimensional dense sensory input. Okay, so that's the input, the X. And then the next step is that it gets mapped to the Kenyan cells where it becomes 2000 dimensional, since there are 2000 of these. And roughly each of these Kenyan cells is connected to a small number of glomeruli, maybe 6 to 10 of them. And the pattern of connectivity looks random. And to a first approximation, it's just adding up those values. So that's where the random projection is coming from. It's simply a result of a random topology, or like a random seeming topology. And so this transformation from 50 to 2000 is can be thought of as just multiplication by a random binary matrix. So you start up with 50 dimensions, and then you multiply by a matrix that's 2000 by 50, where each of the 2000 rows corresponds to one of the Kenyan cells, and that particular row has 50 entries, which basically say which glomeruli it's connected to. So it's got 1 in those entries, and it's just adding up those values. So you take X and you multiply it by this large random matrix. Okay, so that's the random linear mapping. And the next step is that, so now we have a 2000 dimensional dense vector, and now it gets sparsified by just taking the top 5% of the values, okay, roughly. So you end up with roughly 100 values, 100 sparse vector out of the 2000. And, taking precision into account, we can even pretend that it's a binary vector. And so you start with a 50-dimensional dense input, and you end up with a binary, approximately 2000-dimensional sparse vector, where only about 5% of the values are set. And this is the tag that's used for subsequent processing, learning, comparisons, and so on. Okay. And so there's a lot of questions over here. So how can we mathematically formalize this map? What is the geometry of the tag space? So this 2000 dimensional space, what is the geometry of this space in terms of dot products and so on? And what are the beneficial properties of this tag? And so this is basically what we've been looking at in various works. And so what we found earlier is that, first of all, it's a locality sensitive map. So if you look at odors that are close together, i.e. whose 50-dimensional input vectors are close together, then they map to 2000-dimensional tags that are also close together. And so it's definitely a suitable representation for similarity search. Meanwhile, if the odors are even just a little bit far apart, then that distance is magnified. So there's a sort of nonlinear way in which distances are transformed. Close by distances remain fairly close, and slightly far away distances lead to vectors that are almost orthogonal, lead to representations that are almost orthogonal. The second thing we found is that the downstream computations, so for example, we found one of the mushroom body output neurons that was functioning like a novelty detector. And we found some other operations like approximate counting. And all of these were operations that were potentially quite tricky in terms of the original input, but really very, very easy given this high-dimensional sparse representation. And so what I wanted to talk about today was just thinking about the representation a little bit more generically. So rather than thinking about any specific task, just think about universal approximation properties of this. So let's say that there's some function of the input of the X that we want to model, a continuous function. Okay, so how attractive the odor is or something like that. Does this function, even if it's sort of nonlinear in the original input, become almost linear in the expanded input? And that's something that one often hopes for when one is doing basis expansion. And it's something that you find in neural nets, for example. But in the case of neural nets, these mappings have all been learned and are not sparse. So the question is, in this case, even though the expansive map is random and is sparse, do we still get this kind of a universal approximation property? Okay. And how does it depend on various characteristics of the mapping? So here's the setup. So we're going to think of this system as a function approximator. So the X, in the case of the fly, is just the dense 50-dimensional input, okay? But Let's just think of it as any old input, any old d-dimensional input. And what we're going to do is first expand the dimension to some m, which is much larger than d, just by a random linear map, just by multiplying the input by a random matrix. And just to be clear, what happens is that this matrix is random, it's picked at random, but then it's fixed forever. Okay, so it's a random matrix that is thereafter fixed forever, okay? And so the dimension becomes much higher, okay? And then there's a sparsification step, as a result of which we just get a binary vector with only k of the entries set, okay? With only k of them firing. And now what we're going to do is we're just going to look at linear functions of this high-dimensional binary vector, okay? And we're going to try and look at nonlinear functions of x and see whether we can approximate it by a linear function of this c, of this high-dimensional vector. And so that's the kind of universal approximation result that we're hoping for. But it turns out that there are many details here that really matter. And the first thing is, what kind of random matrix is this? Does it depend on the data distribution at all? And so we look at two choices. So we have this random matrix where there's one row for each of these Kenyan cells. Okay, so there's the first row, theta 1 is for this guy, the second row, theta 2 is for this guy, and y1 is just that first row dot product with x, and y2 is the second row dot product. So where are these rows chosen from? So we'll first look at a case where the rows are just chosen at random from some generic distribution, like a Gaussian or, +1, -1. In this specific case, we'll just take the uniform distribution over unit vectors. It actually doesn't matter specifically what it is. The second case we'll look at is where the matrix is data dependent, and we'll look at a very simple form of data dependence where the rows are literally just sampled from the data distribution. And so, there's this kind of weak sort of data dependence in them. Yeah.
It's hard for me to imagine that it's a uniform or Gaussian distribution when it's depend of the parameter input in parameters, right? And the input in parameters are not have the same intensity in each dimension, right? And then why you suppose that have to be Gaussian or normal distribution?
Yeah, so the input is possible, who knows what characteristics it's got, some features might have a slightly different distribution from other features and so on. And so that's why we're looking at these two cases. One where the matrix is actually adapted to the data in the sense that the rows of that random matrix are from the same distribution as the data. In that case, it's adapted. And another where it's really generic. And in both cases, actually, it will work fine, although one of them is better than the other. The one that's adapted to the data is much better in terms of its performance, and we'll see that.
But you select uniform distribution, you change it, the input.
Yeah, so what I'm saying is I'm just going to look at both cases. One where it's uniform and one where it actually depends on the data, and we'll contrast them, both mathematically and experimentally. And in both cases, the data one will be better, as you're suggesting. Right? And that's, yeah.
So when you pick the rows sample from the data distribution, how do you set the prior for that? Like, I'm just trying to understand how you can know the data distribution a priori.
Yes, whatever the data distribution is, it's the same distribution. So it's just like a sort of mild adaptivity to the data, because you can imagine it would actually do something cleverer where it's actually clustering the data or something like that. That would actually be a smarter thing to do, or it's coming up with some sort of covering of the data space. But this is just saying, okay, let's not try to do anything too clever. We'll literally just take things like pick random data points as our vectors instead of actually looking for clusters or something, which would actually be probably the best thing to do. Okay, so it's just that kind of mild adaptivity. Okay, so that's the first the first thing to choose between. You know, is the map random? Like, is it insensitive to the data distribution, or does it depend on the data distribution? In both cases, it's random. And the second is, how is the sparsification done? So one option is that we now have this high dimensional Y, which is dense, and we just pick the top K values and zero out everything else. The other choice is that each of these Kenyan cells is tuned so that it fires approximately K% of the time, or K over M of the time. And so it's got its own threshold, and that threshold is adaptively set so that it's firing, 5% of the time, if we want 5% of the things to be set. So these are two different mechanisms that would both result in approximate k-sparsity, and they have very different characteristics, okay? And we'll see what that difference is. So these are the choices, and we'll just sort of study what this does. Okay, so any other questions about this? Yeah.
So do either of these random linear maps get back to the similarity constraint that you had initially, that you want closer X inputs to map to closer n-dimensional inputs, or these won't really, you are tuning them to
Both of them would do that.
both of them?
Yeah. The locality sensitive property would be possessed by either of these.
Okay, thank you.
Okay. And that'll actually come out in the analysis. Okay, so here's the setup. There's some like data distribution. We don't know what it is. And we'll just say that the data somehow normalize so that they have the same norm. Okay, but it's in the d-dimensional distribution. And now there's some function we want to approximate of the data. Let's just call it f of x. Okay. And we're going to approximate it by a linear function of the z's over there. So we're going to approximate by w1 z1 plus w2 z2. Okay, and so our approximation is going to look like that. I've stuck a 1 over k in the front, but we can just absorb that into the k is a constant here, is a fixed level of sparsity. We can absorb that into the w if we want. So that's going to be our approximation. So the question is, how do we set these w's over here? Well, this is just a regression problem. So we can certainly learn good w's using a standard regression rule, like add a line, Woodrow-Huff, that kind of stuff, right? But I'll also just look at a really naive method where each weight w is just set to the average function value when the corresponding z is firing. So if we look back at this picture over here, if we look at weight w1, let's just look at all the times z is firing, z1 is firing, and just average f over those times. Okay, so it's literally when those two are firing, just average those values. So it's a very naive, simple scheme.
Assume that the weights are just like the 1 over the number of edges.
Yeah, so the f values are real numbers, and the weights are just, what is the average response value when that corresponding unit is firing. So so the weight, for example, between Z2 and the output unit is just what is the average output value when Z2 is firing.
The output or the average Z2 firing?
So Z2 is just binary, 0 or 1, and it's going to fire roughly, 5% of the time. But when it's firing, what is the average function value that we want? And we'll just set the weight to that. Okay, so it's a very naive kind of thing. Doesn't seem like it would be as good as Woodrow-Huff, for example, but it's a very naive mechanism for. Okay. So here's the first thing you can show, and this is just for the simplest scheme. Yeah, basically, each time that's firing, you just take the average value. So, it's a very simple averaging rule.
In the before equation, before here, is no n. Okay, k is n. Why is k is no n?
This one?
Yeah.
Oh, k is, so the thing is only k of these guys are firing. So even though there's m of them, only k of them are actually firing. So there's 2,000 of them, but like only 100 of those guys are firing.
You consider all the elements of the
Yeah. Yeah, everything's in that summation. Yeah, I just put them all together. Exactly. So this is the first result where, so you have a target function, and let's say it's Lipschitz, which literally means that if you vary the input, if you look at two inputs that are some distance apart, the function values are at most that distance times lambda apart. So it's another way of saying that the first derivative is bounded, for example.
Set the weights to the average. Are you doing that? I'm just, is this like online or you set it to?
It could be online. It could be done online. That, yeah, I mean, that's
Yeah,
basically.
what I'm puzzled at is it seems circular. Maybe it's because it's like some like recursive mechanism, but like the output also depends on the weights, right? And then now the weights depend on the output. So that's what I'm.
Yeah. So the weights are the average value of the target function rather than the function that we've learned.
Oh.
So there's it's the target response value. Okay. So if we look at sort of perhaps the simplest scheme where the projection matrix is just random unit vectors, okay, not data dependent, and we're just doing k winner take all. So we look at those 1,000 things and just take the top k of them. Then the error in between the approximated function and the correct function, the worst case error over all inputs, is basically, there's a lot of rubbish over here, is basically k over m to the 1 over d. Okay, so it's k over m to the 1 over d. The other thing you can basically, those are not so important. And so even in this case, there is a universal approximation property. And what this shows is that as the number of Kenyan, or as the size of the representation grows, you get arbitrarily close. And this is the kind of result you have for neural nets. But in that case, of course, it's much more heavily engineered. Like you actually are learning these directions and you don't have the sparsity and so on. So it's a similar sort of phenomenon. So let me just show you a quick experiment over here. And these experiments are very primitive. We're still just trying to work on these. So this is a very simple case where the data is just of spiral. Okay, so it's like a one-dimensional manifold. And the function that we're learning is just a sinusoidal function. And these different colored lines are different values of k, different sparsity levels. So for example, the blue one is a sparsity level of 4. The orange one is a sparsity level of 8, and then 16, and so on, the powers of 2. And at the bottom is the number of Kenyan cells, is the m, which is also growing by powers of 2. And I mean, so one trend is as you get more Kenyan cells, the approximation error is going down. Yeah, any questions about that?
Is it expected that the error is lower for more sparse?
Yes, so that is a great, so that's the question, right? So if we look at this bound, one of the weird things about it is that the higher the level of k is, the higher the error. And we are seeing, it depends on k over m. So, and we are seeing that over here. So over here, this is k equals 4, and this is k equals 8. So this is doubling k, okay, and doubling m. So we can see that actually, like along this line, k over m is constant. M has doubled and k has also doubled, and indeed the error is constant along that line. So in this case, under this learning rule, the sparser the better. Under this very naive learning rule, okay? And so the question is, that's kind of weird, because you think that if it were less sparse, you would be able to do better somehow, because there's more to work with in a sense. And it turns out that is the case if you just use Whitrow-Huff instead. So if instead of learning by this simple averaging rule, you're using Whitrow-Huff, the whole figure is reversed. And now less sparsity gives you a better solution. Okay, and so, okay, because you're actually able to do something sensible with the different features. And so it's no longer a k over m dependence.
Woodrow-Hoff is the averaging rule?
No, Woodrow-Hoff is basically Woodrow-Hoff is gradient descent on the least squares cost function, basically. So it's a more sophisticated rule, although arguably like local. Yeah.
How do you interpret the error? Is it like number of bits that are different between your target and your point function?
It's literally the worst case difference between the target function. It's like the worst case absolute difference between the target function and the thing that's been learned. So this thing is on a spiral, so it's it's compact, and so you can just measure that thing. Okay. So so this was the
And-
bound again.
And the y-axis is much lower in the second plot, right?
Yeah, so
Compared to
okay.
the previous slide.
Yeah, the plots are not, these plots really need to be fixed. Yeah, Gary's absolutely right that in the second one, the errors are lower by an order of magnitude.
Multiple orders of magnitude, looks like.
Yeah. Yeah, and we'll see that actually again when we move to some better choices for the matrix and the sparsification method.
Okay, and while I'm talking, let me say hi to Dave Zipser. Hi, Dave.
Hi, both of you guys.
My first backprop paper was with him.
Yeah. Okay, so any other questions, anybody? Okay, so I'll just say just a few brief words about how the argument goes, and then we'll look at some alternatives, okay? So this is the result. And why is this true? It's a very, very simple argument. So basically, if we look at each of the z's, if we look at each of the elements of the sparse high-dimensional representation, what are the inputs that make a specific unit z sub j fire? Okay, there's some subset of the input space which cause that specific z sub j to fire. Okay, so it's some area, we'll call that c sub j. And because the function is Lipschitz, within this region, f does not vary very much. It just varies by the Lipschitz constant times the diameter of this region. Okay. Okay. So what that means is that if we look at our approximation, which is basically, so x is a particular point here, and there are k of the units that fire. Okay, so x lies in k of these regions. Okay. And so the value at x is just the average of those weights wj, okay? And then each of those weights is just the average value. So the weight wj is just the average value of our target function in this area, in this region over here, which means that if x is in this region, it's not too far from x, simply because f does not vary a lot in that region, assuming the region is small. And then the second observation is that a unit will fire. Each unit has got a corresponding row of the random matrix. Okay, so the first unit has row theta 1, theta 2, and so on. And each unit will fire essentially if that row is close to x, if the dot product between that row and x is high. Okay. And so using that, you can show that in fact, on any input, the things that will fire, the units that will fire will be units whose corresponding theta is actually very close to x within this distance. And therefore, the diameter of these regions is actually relatively small. And so the function is well approximated.
This lambda is that lambda, I remember the Lipschitz.
It's the Lipschitz. You can just think of it as the first derivative of a bound on the first derivative of the target function.
Across all the.
As you're the projection dimension is getting bigger, do you have a sense for are these CJ areas getting, separated out? Is there more overlap or less overlap? Like the receptive field of that neuron has been.
Yeah, so for each X, K of these guys fire. So each X is in like K regions. So they definitely overlap because for each X, K things fire. So each X is in the intersection of K regions. But the regions are getting smaller as you get a higher dimensional representation. And it's getting smaller at approximately this rate over here. This is the radius of the regions. So the regions are getting smaller and smaller, so much more localized. And because they're getting smaller, the function doesn't vary much within that region. So just the average value of the function in that region is a pretty good approximation to the value at X. And that's the argument, basically.
This require the binarized random, or does this work for any sort of random variable?
This would work for, so the same argument would work for lots of different options, like, so this is specifically for random unit vectors, but a Gaussian would also do this, or +1, -1. Yeah, this.
I've lost track of what theta and B are.
Yeah, so theta, so we took the input and just multiplied it by this matrix theta. Theta are the rows of the matrix.
Oh, okay.
So, so the first Kenyan cell is theta1 dot product with X. The second cell is theta2 dot product with X, and so on. And
what's
then we
B?
just keep the highest dot products and hold on to those. And
What's
everything
B?
else gets 0 out. B is just a ball centered at theta of this radius.
Oh, okay.
Yeah, I didn't even define that. Which is not good, yeah.
Sanjoy.
And the question number 2 is missing the Z there. Wasn't it the inner product between W and Z?
So the Z's are 0, 1.
Oh,
And
okay.
and these are just the Z's that are actually firing. So that's why I've restricted the sum to just the Z's that are firing, this X and CJ, yeah. Okay. Okay, so the bound turns out to be something like this. And this is nice in the sense that the error is going to 0, but it's not nice in the fact that it has a very poor dependence on the dimension of the data. Okay, so if the data is 50 dimensional, this is not good at all. Okay, this is an excruciatingly slow rate of convergence. And yet for a lot of sensory data, we often expect that it lies close to a lower dimensional manifold. And so the question is, what would happen then? Like, let's say that although the data seems to be 50 dimensional, odor space or whatever is close to a much lower dimensional manifold, maybe 5 dimensions or 10 dimensions. What is the D over here? What matters? Is it the 50 or the 5? Okay, so that's the question. And unfortunately for this method, it's the 50. Okay, and here's a picture of why. So let's say that the data actually lies on this really low dimensional manifold, like dimension D0, okay? But our rows of the random matrix are chosen from the full space. So they're just all over the place. So we can think of each of these dots as being one of the rows of the matrix. And when we get an input, the units that fire are the ones whose dots are close to that input, which means that there are a bunch of units out here that just never, ever fire. Those units are completely wasted. Okay, so even though there's a ton of them, they will just never fire. And that's why this particular setup does not adapt to manifold structure at all. Okay, so there are 2 ways around it. The first is to do a different type of thresholding. Instead of doing this K winner take all, where you just take the top K values, do something different. And the second is, don't generate those rows from some full dimensional random distribution, but generate it from something that's closer to the data distribution, like something that looks like it kind of lies along the manifold as well. And both of those solutions work. Okay, and let's just see what bounds we get in that case. Okay, so the first solution is that instead of doing this winner take all, where we just take the top K values, the problem with winner take all is that there are some units that will never ever fire. because their corresponding row of the projection matrix is very far from the input space, and they will just never fire. So instead, we force every input to fire 5% of the time, or K over M of the time. We just give each unit a threshold, and that threshold is set so that it's firing 5% of the time, and so nothing's wasted. Okay, so it's something where in expectation, you still get 5% of the things firing. It won't be exactly 5%. Sometimes it'll be more, sometimes it'll be less, but on average, 5% of them will fire. Everybody set their own threshold, and now everything does fire sometimes. Okay, and so the picture over here is that if the data lies in a low-dimensional manifold, and these rows of the matrix are very far from the manifold, still they will fire. And the inputs on which they'll fire are literally the closest inputs, which for this guy is, just drop it at right angles onto the manifold, and then look at those points right there. And like take roughly 5% of the data distribution around there, and those are the points for which it'll fire. So everything fires.
Let's see if I might be forgetting some of the responses here. So X is the space where the data lies?
Yeah.
And then these data are the first ones, like when you go from X to Z.
Exactly, and the thetas are in the full dimensional space. So even though the data lies in a low dimensional manifold, the thetas could be really far away from them. But now every unit is forced to fire. So even if its theta is very far from the data, if we project it onto the data space and just look at the data points around there, it will fire for those data points. It'll fire for 5% of the distribution around that projection, basically.
What? Sorry.
Projection is literal. By projection, I mean literally find the closest point in the data manifold.
Oh, so instead of using the actual data you had, you're using another data that is the projection on the manifold.
Effectively, that's what's happening. Effectively, the thetas are being projected onto the data manifold. Although, because we're using L2 distance, it doesn't matter. They're the same. But yeah, effectively, that's what's happening.
And in practice, what it is?
It's literally just the dot product, so there isn't a projection taking place.
Okay.
It's literally just the dot product.
But in this case, you is considering the spontaneous emission in the case that.
Yeah, so in this case, what's happening is that the threshold for each unit will have to be set adaptively, so that it's firing about 5% of the time. And so that's something where, if the data is coming from some sort of stationary distribution, if it's stable, it'll stabilize quickly, but otherwise it might need to continually adapt, which is, it's not very hard to sort of track the 95th percentile of a number. So that's not that tricky.
Do you have any control for the magnitude either of the input or of the data, like the norm of those vectors?
Yeah, so here the assumption is everything just has a length of 1. Everything has a norm of 1. The data, as well as the in this case, the thetas are being drawn from a uniform distribution of a unit vector, so they also have norm 1. So that's kind of out of the equation, because everything's based on dot products. So things have to be normalized, otherwise there's trouble. Okay, so and so if you do that, you get the same bound, except that now it depends on the manifold dimension. So exactly the same thing, but now it's a manifold dimension. And so it's adaptive to that. The other thing you can do is to actually have the random mapping depend on the data distribution. And so here, the rows of the random matrix are just picked from whatever the data distribution is. Okay. If you do that, again, you get the same bound, but with the with the manifold dimension. Okay. So both of these methods work to adaptive dimension. The original method is not adaptive because a lot of the units are not used. And so there are two solutions. Either you sample the rows differently or you threshold differently. Okay. And here's a Okay, again, these graphs are on completely different scales, but on the left is what we had before with winner take all, and on the they're both winner take all. On the left is what we had when the rows were random unit vectors, and on the right is what we get when the rows are sampled from the data distribution. And these are terrible pictures, but basically over here it's 10 to the 0, over here it's 10 to the -4. So there's like a 4 orders of magnitude difference. It's just much, much better to sample from the data distribution. It's just a huge difference between those two things.
And that seems to be a critical phase transition, right? There's this big drop that happens beyond a certain value of n in all cases.
Yeah, so right, so over here, it looks like some sort of K over M phenomenon, like M has to be at least a certain size relative to K. But this is just for the naive averaging method, and for Woodrow-Huff, it would be something different. Yeah. So that's actually all I had. I wanted to end with like this little graph over here, which I found very interesting. So this is from the actual this is the actual sort of random projection matrix. And we've been talking about all these random matrices. This is the actual random matrix where the glomeruli are along the horizontal. So there's 50 of them along the horizontal. And on the vertical, you have just 200 Kenyan cells chosen at random, okay? And you can see the pattern of connectivity. And it looks pretty random, but the thing that is very striking about it is that some of the glomeruli are represented much more heavily than others. So some of them are sort of overrepresented, and that's kind of interesting. Why is that? What are the benefits of that? It's not something that we modeled at all, but it's something that's it's clearly a very significant effect over here. And so that's something that is sort of a curiosity.
Can you just repeat the curiosity?
Yeah, so our model was that each Kenyan cell just chooses a few of the glomeruli at random, and that's the connectivity pattern. But if that were the case, then each the degree of the glomeruli would all be roughly uniform. But that's not the case. If you just look at these, so because each of the columns is glomerulus, and some of them are much more heavily represented than others. And so the question is, what is going on over here? Why are they more heavily represented? Presumably it is beneficial in some way. And when one is doing random projections, this is not a common sort of thing that gets built into them, where one of the features is much more highly weighted than another. So it's kind of interesting.
Yes. But nowadays we have to connect them. Do you know if across individuals it is completely different?
Yeah, so this is actually an old picture. Yeah, so this is a picture where each row was obtained by just picking, because the glomeruli are identified, but each row was obtained by picking a Kenyan cell at random, seeing what it's connected to, and then the fly dies. And then you bring in the next guy, and then, so each row is, yeah, so so I don't know what the updated picture would look like.
Just wanted to add one quick point. Maybe it has to do with energy efficiency. I mean, we always should keep in mind in all these synchronies or different levels of contributions of them, we may also somehow incorporate information theory there and see if there is some levels of energy efficiency, efficiency in coding, and then equivalently energy efficiency is happening there by that mechanism.
So in this case, like, would energy efficiency be related to sparsity? Is that how it would be manifested?
Yes, definitely, but the fact that what you are surprised is some of them more contributed. You see a stronger activity by them, so maybe it has to do with energy efficiency. I mean, it should be transformed into a information theory setting, and then we need to have an upper bound, the maximal entropy distributions or a maximum information setting, and then we compare the current distributions of these activities to that maximum, and then we will find a criteria if it's energy efficient or not.
Yeah, that would be really interesting if there was some sort of explanation of that type.
Because always because the brain works with a very small amount of energy budget, we always keep in mind anytime we see something, a pattern we always keep in mind the fact that maybe it's the fact of energy efficiency and information efficiency is happening there for the sake of saving energy, that mechanism naturally happening.
Okay. Yeah, that's a dominant consideration, huh?
Yes,
Yeah.
yes, and I have seen that in different scales of brain processing. We have done it on synaptic weight with Terry at Salk, and then different scales also I see at the circuit level, neural activity level. We see some efficiency coding, some of the information and efficiency coding is happening at the time varying at the circuit level. In our case, at the synaptic level, we saw energy efficiency happening. So different scale of the brain is trying to do that to eventually achieving having 20 watts of energy for energy budget of brain processing.
Okay, yeah, that's interesting. I mean, this setup over here is actually a very simple setup. And so this might be a case in which it's possible to actually flesh out this kind of argument. There's
Yeah.
not a lot of moving parts over here.
Exactly. Yeah, I mean, you have the papers online. I should look deeper into them, the set of the papers you described. Thank you.
Is how it's affected by the in. And this is, you can see the input in this case. It's changed that's distribution.
So, right, so looking at this, it might seem like you know, some of the input features are perhaps different from others, which would explain, you know, why there's this kind of selection going on. But actually, when the inputs are considered, when the glomeruli are considered individually, there's a sort of normalization that's taken place where they all have roughly the same looking distribution. So just by looking at the marginal distributions of the input features, one doesn't see an explanation for this kind of thing. It's not, you know, it hasn't. I guess that this might be a way of magnifying certain inputs that are more important. I mean, that is the effect that it has. And what's not clear is how it plays into the overall randomness of the process.
So the columns are inputs, right?
The columns, yeah.
It looks like some of them have no connections at all. I'm just kind of curious if
they might have connections because this is a very this is older and it's a very imperfectly sampled, you know, and this is not down 2000, you know, this is not, yeah.
these are any cells.
In the rows, yeah.
So what if in the sparsification step you do like a noisy top K instead of a top K? Would that potentially help with the sort of reachability issue that you showed in one of the slides with your figure? I don't know, maybe you'll get some dot products that are like away from the data distribution that might help somehow. I don't know.
So if you did a noisy top K, it would help a little bit, but it would have to be like a really, really noisy top K
Okay, yeah.
to actually get around the fact that, you know, some of those thetas are really far from the data manifold. So there would need to be a very, very high level of noise.
So one is, so you showed the error right? Like for the K versus M in the beginning, like very beginning of your talk. And I'm trying to recall here, like everything you told us, and then you showed again the same figure. And I'm trying to, I think I don't, what was the difference? Like, what did you do between one and the next? What's the difference? Is this just because of the next part is in the data distribution? No, right? Because you already have both of them here.
Yeah, so the difference between these two is on the one on the left, the random mapping is picked just from a uniform distribution.
No, yeah, between these two, yeah, uniform here and then the data distribution here.
Yeah,
But
yeah.
then are these the results you show in the end of the talk, are they the same or is this different simulation of the one that previous slide? Did you show those plots again? Yes.
Oh yeah, so these were the last ones. And the ones earlier were just the effect of moving from averaging to Woodrow Huff. Yeah, so
I see. So the second part of this, so everything after this was with the data distribution?
was the manifold, yeah. Was just kind of how do you deal with stuff that's on a manifold.
And that was so that you could set your weights to the data distribution.
Well, not so much the weights, but that the actual random mapping is adaptive to the data distribution. And that makes a big difference if the data lies on a manifold. Because if the data is on a low-dimensional manifold, and the random mapping is somehow adapted to that, then it's actually able to get close to the manifold instead of just being very far away from it. Because a manifold is like almost, I mean, it's almost, it's, you know, it's zero of the overall volume. And so.
Okay. Okay, then I definitely got lost on the math. In simpler English, what was the solution then? So the challenge was to make the weights such that the projection is adapted to the manifold. And what was the solution to that?
Yeah, okay, good. Yeah, so the first bound was just in the case where the thresholding is done by taking the top K values, and the actual expansive map, the linear map, is based on a random matrix whose rows are just random unit vectors, completely not dependent on the data distribution. And we saw that this, you can give a bound for this, but if the data lies on a low-dimensional manifold, this cannot adapt to that. The bound just depends on the underlying dimension, which could be really high. So in order to adapt to that, you have to do one of two things, and either one of them will work. Method number one is that expansive map, that matrix, that random matrix, instead of choosing random unit vectors, just choose stuff from the data distribution, or just anything closer to the data distribution. And that makes all the difference.
So that would force certain seeds to fire. And the other method you're saying is you can still use the random unit vector weights, but you would like kind of somehow manually force.
It's not so much manual, but yeah, the other method is that each Z by itself maintains a threshold so that it fires 5% of the time. So each of the Z's just individually decides, I'm going to fire 5% of the time. I got all these values coming in. I'm going to look at the 95th percentile, and whenever it's above that, I'm going to fire. So that way everything's useful, everything fires, and that also works. Yeah, either of them gets the job done.
So I really enjoyed like how you have these choices and you compare their bounds, but do you have a sense for which choice the fly made in its application? Okay, but this is just a way to compare different ideas to see, hey, if you had the dimensional of the manifold bounding versus you were scaling with the one over K, it could actually impact a lot, right? The orders of magnitude.
Yeah.
But, thank you.
No, I have no idea about that.
Oh, so this might be a little tangential to your talk, but I was wondering if you have any comments about how maybe you could do computations in the sparse space. So let's say if I have to like subtract, so if I subtract two sparse vectors, do I also get the subtraction of the target function at the end? Or
so in the sparse space, yeah, the main operation is the dot product.
Yeah.
And that can be related to operations in the original space.
Okay.
But yeah, the main thing that's going on there, the main thing that's preserved is dot products. And basically vectors that are close together in the X space
Yeah.
have very high dot products in
Right.
the, and
that
otherwise they
makes me
become
think
almost
it's like
orthogonal.
an embedding of some sort, so.
It
It's
is,
an
yeah.
embedding space, then maybe computations and some inference. what we're seeing.
Yeah, you can do, but the thing is that, you know, it's all 0, 1. So
Yeah.
it's a binary thing. So dot products make sense.
Yeah.
But I don't know what happens with subtraction, that kind of stuff. Addition makes sense.
What if you do the computations in the non-sparse thing and then sparsify it and that? I don't know.
Oh, so if you do computations before sparsifying,
Sparse-
and I'm not sure.
Yeah. Yeah.
Another question there, because it's not dependent of the time, right?
Sorry?
It's not dependent of the time.
Of
It's independent of the time.
Yeah.
It's static in this case.
Yeah,
and
it's
then
static.
Only you consider the separation between the signals or the preparation of this one. Yeah, but in the reality, you need to consider the time, right?
Yeah, so I think that all of these, all of the stuff that's going on, even with a fixed random matrix, it is actually quite easy to adapt to a time varying signal, you know, to a time varying data distribution, because the statistics being maintained are very simple. It's literally averages and percentiles. And that is something that one can very quickly adapt to if the distribution is changing. It's not a sophisticated statistic over here. So tracking a changing average is very easy. Likewise, the change, you know, yeah.
And sound good, because you know that if you get some cell is send the signal, and probably the next cells is not possible because don't have enough energy to send the signal, and this affected that happened in the eyes, not that in the eye, that happened.
Yeah, so I think that I mean, just in terms of like you know, things failing to fire, etc., you know, that high dimensional representation has a lot more robustness. Because even if there is you know, one of those Z sub J's that fails to fire, there's something else close to it that is firing and has roughly, you know, the same associated value. So there is a kind of, you know, and that's not true of the original representation, where losing one feature could actually be quite impactful. So
and then give you the capacity to give plasticity, you know, in that case, because that's happening in some points that is moving in other direction because the dimensionality is higher.
yeah, so I think it would be interesting to actually see how robustness changes between the original representation and the higher dimensional representation.
Do you think that this kind of structure to the problem is something special for olfaction, or is it used across the brain?
I actually have I have no idea. This seems actually this is actually a very common structure in other settings. You know, it's very similar to, say, like kernel methods in machine learning and so on. So it was just interesting to find something. The main difference here is the sparsity, which is not a feature of, you know, kernel, you know, its uses in other settings. But this kind of basis expansion, you know, idea is all over the place in machine learning. The sparsity is kind of a new thing over here. In terms, and that was the part of the analysis that was a little bit different.
Would it be fair to say in moving from the winner takes all to the essentially percentage of firing approach, like the thresholding approach, would it be fair to say that you're changing the dimensionality of the discrete jumps from the high dimensional space just to the manifold space, in the sense that if you go to essentially a closer Z from in the winner takes all scenario, essentially like you've lost a whole dimension, like the whole input space's dimensions worth of a factor by turning one off and the other on. And then in the thresholding approach, you're essentially, you can have as many on as is reasonable, so long as they're within that like 5%. So it's essentially follows the manifold more before it discretely like turns off.
Yeah, I
Is that
think
kind of
that
a fair way
I think that the representation produced by thresholding is a little smoother
Yeah.
in that sense. I do think so, yeah.
What made you choose the spiral and the sine function? Do you have, is this like, if you vary that, do you expect to have any changes? Can you just comment a little bit over?
No, we should have tried a whole bunch of things. You know, this was just a fairly arbitrary choice. You know, it was something that seemed both simple and somewhat uncontroversial, you know. And so we just kind of chose that, but no doubt we should have tried a whole bunch of different things because, you know, each example brings up interesting new stuff. And in particular, there's none of these examples sort of bring up the effect of low dimensionality. And so that's something that we do need to explore, you know. So we're going to look at experiments where the ambient dimension is very high, but the manifold dimension is very low. And something to really show that the methods are different. I mean, we just did that kind of mathematically.
The idea of the spiral is to be a 1D manifold in a 2D space.
Or in actually, we did spirals in any dimension, and it turns out the pictures don't change.
Oh,
So the weird, yeah, the pictures don't change. So if the manifold is the spiral, even the naive method adapts to that. But there are other manifolds to which it does not adapt. So we really should be finding one of those and, you know, sort of like demonstrating that.
You don't need an application. Oh, no. How do you know that it's okay?
Why are happy? Why are happy, right?
Yeah, I don't know. I mean, I tend to understand things just through the equations. That's kind of like the things that make sense to me. But yeah, it would be nice to just have a few more experiments and see, you know, like what happens really.
Are there what are some non-neuroscience problems you think these sparsity considerations would be useful for?
Okay. Would they be useful in a non-neuroscience context? That's a great question. Yeah, I don't know. I work a little bit with people who do this kind of you know, these ML on embedded systems, and you know, there is some desire for sparsity there, but it's a different type of sparsity. It has to be structured in some way. It's not just, you know, to sort of be more localized. Yes, I don't know.
Just wondering here how to stretch this approach, like until it might fail. For example, would you expect if the input manifold is higher dimensional, would it be harder to do it, or like how exactly would you make it learning harder and to see when and at which point it might not learn anymore?
Yeah, so I think that if the input manifold is higher dimensional, then the number of Kenyan cells required would be huge in order to model kind of arbitrary functions. But that is kind of inherent. There's no trick that can solve that problem. That is just you know, a lower bound on learning you know, arbitrary like Lipschitz functions in high dimensional spaces. There's no way to finesse that.
Huge to a point that the brain wouldn't have it, that would, is that the huge mean?
Um,
So for example, I'm thinking of like, there's a fraction, I don't know how lower dimensional fraction is, but like, I'm also thinking of vision, right? Like, it's, I mean, there's structure in the visual world, but, it's not 1D, it's not 2D.
oh, yeah, yeah. No, I think that, yeah, so I think I see what you're saying. Yeah, so I think that, so this is just talking about manifold structure, but of course there are other types of structure in data, and it would be good to exploit that. But unfortunately, we don't really have words for a lot of those types of structure. We know about manifolds and we know about clusters. And once it moves beyond that, we don't have the words for it. So we know there's structure there, and we know that somehow deep learning is able to capture some of that structure, but we don't even have definitions for a lot of this structure. And until we have that, we're kind of at a loss. It's just something, it's just out there.
So let's transition to the tea time. Let's do go in the dark.